Okay, now we're going to finish up the second part of the human movement notes by looking specifically at the concept of a tracking loop. And I hinted a little bit in the first part of motor skill notes about a tracking loop when I described pointing to a target in the concept of the speed accuracy trade-off in Fitts law as a feedback loop. And so we need to maybe think a little bit about what a feedback loop involves. So if I am trying to, let's stick to the case of reaching. If I'm reaching to push a button, what I have to do is I have to generate a command in the brain that determines the appropriate degree of muscle contraction of all of the relevant muscles that control my arm to get it going in the right direction towards the target, as well as traveling the right distance towards the target. And the distance, of course, is determined by the amount of muscular force involved that might propel my hand a large distance at a higher acceleration, or a short distance at lower acceleration if the target isn't quite so far away from me. That initial muscular contraction is based on visual information that I have available to me at the beginning of the movement, right? I have to visually perceive how far away the target object is and where my hand is relative to that. And so how much distance my hand's going to have to travel. And that determines the scale of this kind of force output that is generated by the muscle contractions that has to be calculated in the motor areas of the brain. Now, if we have a situation where this system is perfectly calibrated, and by that I mean that my judgment of the distance to the target and the size and direction of the target is all absolutely 100% perfect, and my brain is able to take that perfect information and generate a perfect muscle contraction that will just get my hand where I want it to go, and I don't have to think about it after that. I just, everything that is all predetermined at the beginning. And then the movement is generated and pre-programmed and then just launched. That's not a feedback loop. That's actually called feed-forward movement, where basically everything about the movement is planned in advance, and then it just goes off without a hitch. And like I said, of course, it relies on high degree of perfection here, right? We need absolute accuracy and precision in localizing targets and generating these muscle contractions to generate the appropriate movement trajectory. Most often, that's not going to be the case, that we can compute these kinds of things and be so absolutely exact with our pre-planned movements. So instead of a feed-forward system, so what that is called feed-forward because of the idea of the generated motor command feeding forward into the movement, and then it just occurs like that as it's planned. Feedback, on the other hand, means that we have some of that forward-generated movement trajectory, movement plan information, but then the results of our movement are fed back to the brain so that they can be evaluated, and then we can use that to determine whether that movement needs to have a correction applied to it. So we're going to do this feedback loop sort of what we call on the fly or online, right? So there's a difference between online correction and offline correction. So let's think about that for a second. With offline correction, what I do is I'm going to pre-plan the entire movement. I'm going to reach out there and I might hit the target just as I had desired, in which case I'm going to have what's called knowledge of results at the end, right? And that means that's going to tell my brain, good job, everything's working, right? And that's an offline piece of information because the movement's already done, right? Or I might miss the target, in which case that might need to go back to the brain and say, the next time you do a movement like this, maybe you need to recalibrate how you plan this movement and make some changes to how that movement was planned, but only in the future, right? It's not going to correct the one that just happened, but we're going to relearn and correct future movements, right? So these are called offline corrections, because these are corrections that are essentially applied after the movement is completed and only apply to future cases. So it happens between the movements, right? Not while a movement is actually happening. So in an online correction, that means we're going to change the movement as it's happening. So that is, as my hand is moving towards the target, I'm going to try to continuously monitor the trajectory of my hand moving towards my target. And if I detect any deviation in accuracy, if I'm going in the slightly wrong direction, or if I'm approaching too fast or too slow, then I'm going to make the appropriate adjustment. And that's an online feedback control. And this is where we talk about a tracking loop, right? Because in this case, what we're doing is the feedback is considered a feedback loop, right? The idea is I send the command to the hand, but then as the hand is doing its thing, information is looping back to the brain to evaluate the state of affairs. And then we evaluate, do I need to continue where I'm going? Everything's fine, or do I need to make some sort of adjustment or correction to the movement as it's happening? So this means that we're going to assume we're going to have some visual control of the movement. Now, this applies to us controlling our body parts like hands and feet and so forth when we reach to touch objects or kick things and so forth. But it applies every time we operate any kind of device, right? So when I use a computer mouse to control the cursor on the screen, again, I am moving something with moving my hand, but there's a visual consequence, which is, does the pointer go where I want it to go, or do I need to make a correction? If I'm steering a car, I make, again, a control input movement by turning the wheel, and the car is going to respond by turning some appropriate angle, and I need to evaluate whether I'm understeering or oversteering as I complete my turn. And the same goes for speed maintenance, which I've used as an example many times in previous notes, that I'm going to step on the gas pedal to speed up perhaps because I think I'm going too slow. And I need to evaluate, when have I sped up enough and when is it time to back off the gas pedal, or do I need to keep going? And the same goes for braking control, by the way. As I'm braking to come to a stop, I have to continuously evaluate whether or not my rate of deceleration is appropriate to stop where I want to, or do I need to apply more or less brake pressure. Anytime we are teleoperating any kind of technology, telerobotics, unmanned aerial vehicles, unmanned ground vehicles, any remote operation of a device, telesurgery, for example, these all involve control display loops, right? And the same even goes for a laparoscopic surgery as well. Speaking of telesurgery, when a surgeon does laparoscopic surgery, the tools are inserted into the patient's body through a small incision, and there are tools that the surgeon can manipulate with hand controls. So they just have these weird hand controls that they hold up in front of themselves, and they're looking on a video monitor typically, because there's also a small camera attached to the end of their tool, so they can see the tool and the inside of the patient's body, whatever organ they're operating on a video screen. And so again, movements of these hand-operated tools that the surgeon holds have an output on the screen. And so again, there's another feedback loop here. Obviously, we can be concerned about stimulus response compatibility for all of these kinds of settings here, but we also just want to understand the nature and the dynamics of the tracking loop in and of itself, and how this feedback information works, and how it can be very important consideration to our levels of accuracy and movement speed even. So there's a variety of technical terms we want to first define. First, we need to have what we want to call our desired state, right? So desired state might mean hitting the button that I'm trying to push, or getting the cursor over an icon that I'm trying to click on. Or if it's speed maintenance, it means hitting a target speed that I want to achieve when I'm driving my car. So we're going to design that as I. So I is our desired state with the subscript C here, because we're trying to control that. And it can vary over time. So we're going to give it a time index, because if I'm driving a car and I'm in one area where I decide that I want to go 60, and then driving conditions change, so I want to move to a different desired state, like say 40 miles per hour, then obviously, then I is not a constant here. So one of the things that we need to do is detect deviations between our desired state and our actual state. And that's considered an error state, right? So our goal here is to always reduce error. And so error is defined E. And of course, it varies over time as well, because sometimes my error might be 0, right? I'm actually at my desired state. I'm maintaining my desired speed. But sometimes I might be off from my desired speed, right? I'm starting to slow down and I need to step a little harder on the gas pedal maybe, right? So I have error. And so when I detect error, that means I need to have a response. And this means in order to input the response to the system, I have to apply some degree of physical force to the controller. And so that's our F, right? So that means, of course, speed maintenance means I have to actually use my foot to apply a force to push down on the gas pedal, or if I'm steering, I have to apply a physical force to the steering wheel. If I'm using a mouse, I have to apply a physical force to the mouse to move the cursor on screen. And that will vary over time as well, right? So again, we have a time index on our force. But then we also have to think of something else here. And what's the relationship between the response and the output? And that's the force and the output. So a certain amount of force applied to my controller will result in the controller moving by a certain degree. And that is called U, right? So how much the controller responds to our input is the controller output, right? And that's U. And what this refers to essentially is how much the controller might resist its operation, right? So if you have a car with power steering, for example, then what you notice is that the steering wheel is very smooth and easy to operate. It doesn't require a heavy amount of force to turn. But if you have an old car that uses what's called rack and pinion steering, it doesn't have a power assist, and so that means that the physical force of turning the wheel is directly related to the physical force required to actually operate all of the moving parts of the steering linkages and get the wheels to turn. And one thing that you'll notice in driving such a car is that when the car is actually rolling forward with some degree of forward momentum, it's relatively easy to make a turn. But when you are sitting still, it requires a great deal of physical force to turn your tires, right? So for parking, for example, in parallel parking, when you stop and turn the wheels, you really got to crank the car. The car I had in grad school a million years ago was rack and pinion, and I remember struggling with that, right? So that's called your control dynamics, which is basically, what kind of dynamical forces are required to actually physically move the controls themselves. But then once you get the controls moving, the next question is, how does the system respond to the control operations? And that is O, right? So now we have a mapping not just from F to U, but from U to O, right? So I apply a physical force to the controller. The controller will respond by moving by some amount, and then that's going to cause a change in my system. And that's my system dynamics. And so ultimately, that's also what I'm interested in here, because I'm trying to alter the system dynamics so that way my error ends up at zero. So I want my system dynamics to match my goal state, right? And once I'm able to achieve that, then I have reduced the error to zero. But on the other hand, if I continue to detect additional error, I'm going to continue to go back and apply another force to the controller, which will then change U and then change O. So there's a complex dynamical relationship here. After I have detected an error E and applied a physical force F to the controller, then the controller and then the system will respond accordingly. And hopefully that reduces E, but only if I have properly operated my control. And so if I have improperly operated my control, then I might increase E by going in the wrong direction, right? Maybe I'm supposed to be turning more to the left, but I ended up turning to the right, and I did some weird incorrect steer while I'm trying to steer my car. But then there's also the possibility of sometimes my control inputs being too weak, right? So if I'm trying to steer to the right to make a right-hand turn, but I don't turn the wheel enough, then even though there will be a system response that will minimize the error, will reduce my error, it still is not error of zero, and I'm going to end up perhaps understeering. And then there's, of course, the possibility that I have applied an input to the control that's too strong, in which case I overshoot the mark. And even though I might go towards zero error, it actually then flips and ends up having an error in the opposite direction. And we might call that oversteering, right? So if you've ever, when learning to drive a car, you might sometimes notice that when you turn, you end up kind of wiggling a little bit after you complete a turn because you kind of oversteered a little bit, right? So that would be a case where you applied too much input to your controller. And so as I noted before, there could be a system where you might have the ability to do a feed forward type of situation here, where once you detect the error in the system, you know exactly how much physical force to apply, and you apply that exactly and precisely the way you need to, and that results in the control and the system responding perfectly so that you get zero error at the end of it. But odds are you're not going to be so good at this, right? So that means that even though every time you input a response into the system, it might generally reduce the error, but it doesn't necessarily totally eliminate the error. So that means you need to continuously monitor, and this is where we get into online control here. You need to continuously monitor the error states and make continuous responses to continuously operate your controller, right? And this is why we're going to call it a tracking loop, because of this continuous operation of error detection and response inputs. What I've just described is typically referred to not just as a feedback loop, or what we might also call closed loop control, because of the idea that when that information, I send the information to the system with my response, but then the results feed back to me. And so that's the closed loop. But it's considered a negative feedback loop because of the idea that the way in which our responses work is always in a way that opposes the state of the system in terms of the presence of error. So consider an example of lane maintenance. If I'm driving my car and I detect that the car is drifting to the left, then I want to steer in a way that's the opposite of that error, right? Which is steer to the right. But if my car is drifting to the right, I steer to the left. Back in the notes on haptics, when we were talking about postural control, that's another negative feedback loop, because if I detect that I'm falling forward, and maybe it's visual information in the moving room studies that caused me to detect that, then my response is to fall backwards, is to lean backwards, right, to counteract my forward lean. So again, in those situations, we're seeing that people are all engaging in a way that's opposing any detected error in the state. Notice also that that error comes from two sources here, right? So there can be a change in what's called the command input. So I said before that our little subscript C is the part that we're trying to control and command the system into this state, right? So I decide that I want to go 60. So because that's a speed limit and that's the traffic and supports that speed. So I say, okay, I want to go 60, but then maybe traffic slows down or I end up on a residential street. So I say, now I need to go 40 instead, right? So that's a change in my desired state or command input. But there can also be disturbance inputs as well, right? And so in this situation, if you're driving a car and it's windy, then maybe your car is just kind of wobbling in the lane because of really hard crosswinds. And so that's kind of that you're trying to maintain this state, but something's always pushing you out of that state, right? So there can be all kinds of these external disturbances to the state that you're trying to maintain, and you have to correct for them, right? So you either have to correct when your desired state will suddenly change for some reason, or you have to correct when there's a disturbance that knocks you out of your desired state. So a couple of things that we want to think about here is related to the system dynamics, right? The relationship between a movement of our controller, and that's the controller output U, and the effect on the system O. And this is where, again, we could talk about some of these control display relationships, but in this case, it's more of a control system relationship, right? But when in the previous notes talking about controlling using a mouse to control a cursor on screen, that's a control display relationship, and it is a control system relationship. In this case, the system that you're operating is the pointer itself. But in other cases, the system might be, of course, the speed of your car, the deceleration of your car, the lane position that you're trying to maintain, or any sort of remotely operated tool that you're controlling, right? So we can come back and think about some of the same terms we used in the mouse control set of notes, like positional gain, where there's a constant sort of fixed ratio relationship between movement of the controller and movement of the system, right? This is also referred to as zero order control or positional gain, right? The reason it's called positional gain is that what you would say here is that the state of the system or the position of the system is in some way directly related to the state or position of your controller, right? So in that case, again, the idea is that, like I talked about with a mouse, If you move the mouse 2 inches on your tabletop, the cursor moves 2 inches on screen. That's a direct relationship between position or change of position in one object corresponding directly to the position or change of position of the system and how it responds to it, right? Now, we can also have first order control, velocity gain. And this is what I was also talking about with the idea that what we're going to do now is we're going to let the position of our controller change the velocity of our system, right? So we can ramp up the gain to go high velocity when we want to go a long distance, like moving across a large screen, but we can slow down the gain and go low velocity when we want to acquire a fine small target on screen, right? And so that would be one advantage of having a velocity gain kind of setting in a system like that. But then there's also second order control or acceleration gain. And so here what we're going to see is that changing the position of the controller directly results in a change in the acceleration of our system, not in its velocity or not in its position, but in how that system accelerates. And what we're going to see here is that every time we go to a higher order of control from 0 to first to second, we're introducing a little bit of lag in how that system responds, right? So think about this, for example, if you've ever operated a boat, a big boat especially, right? Maybe a big yacht or something, right? When you move the throttle forward, that applies more power to the engine, and then the engine kicks on and you start to accelerate. But then it takes a minute for the boat to get up to full speed, right? It accelerates up gradually towards a maximum velocity. And then at some point you might realize, oh, I'm going too fast for the conditions we're in, perhaps, right? And that's because it was difficult for you to predict just by how far you move that throttle lever forward, how fast that boat's going to go, right? And especially since it takes a few minutes or maybe at least 30 seconds, at least before your boat gets up to that speed, your ability to detect the oncoming error is reduced because you don't know that you're going to end up going too fast until several seconds have arrived. And by then what you have to do is you're going to have to pull back on that throttle again to slow the boat down. And again, if you overdo this, right, now you pull the throttle back and gradually the boat slows down. And then you realize, oh, I'm going now slower than I want to go, right? So this ends up resulting in what we might call an oscillatory situation, because you're always either over accelerating or under accelerating here. And so it's a little harder to control these kinds of second order systems. I used a little slightly less common everyday example here called under rocket thrust, right? So if you have a rocket in space, you know, you're piloting a spacecraft, one thing you can do is have a button that kind of activates, you know, some kind of a booster rocket, right? That will get you moving in a specific direction. And maybe the length of time you hold down the button determines the length of time that the rockets fire. So one single hit of the button will cause the rockets to fire, and that's going to trigger an acceleration, and then that's going to take some time for that to really get the whole entire ship moving, because that acceleration has to overcome the large inertia of this large spacecraft, or in the case of the boat, like I said, right, there's a big heavy boat and with water resisting it. So it takes time for all of that inertia to be overcome and to get this heavy object accelerated. So maybe that one single bump is not enough. So how long do I have to hold the button down? And that's tricky to determine, right? Unless I'm well practiced, right? So the text on this slide is kind of describing this kind of sluggish, laggy system that's slow to respond to your control inputs. And so the idea is that, like I said, by the time you notice the fact that you have overshot the mark, your system is now going to have a large error. So you have to then always try to counteract that. And it tends to result in this oscillatory function that we could say is not a very stable system, right? You're always having some degree of error. You're always undershooting and overshooting your error because you don't know how long to hold down this button in order to get the desired acceleration state out of your spacecraft or rocket or boat, right? So here's just another example of a second order system that, as you can see, the output of the system O is a function of this kind of second order dynamic. And this is a weird case, again, it's not a very realistic situation, but imagine you have a plank, right? Just a board, like a 2x6 board. 1x6 board maybe is more easier to think of it here, right? And you have something on it like this thing is supposed to be a rolling soda can, right? And so your task here is, if you tilt this board one way or another, I know you can't see me in the camera frame here, but if you tilt this board one way, or I'll use a book maybe as an example here, if you tilt it one way or another, that can is going to roll from one end to the other, but your task is to try to get it to stop so that it will balance right in the center here, right? So of course, if you stop too soon, it's going to roll back to one end, and if you stop too late, it rolls to the other side, right? So as that can starts to roll, it picks up acceleration, and then you have to counter rotate your plank in order to get that thing to stop accelerating right at the point where it will stop in the center, and you can get it balanced halfway between the two ends, right? And that's the nature of this kind of a laggy second order system, is graph C here, where after controlling the input, which is the sudden step change in the dashed line, the system gradually and slowly responds to get to that state, right? In position control, that sudden input change on the dashed line is matched by a specific step change in the output of our system, right? In velocity here change, the idea is that there's a different ramp, more of a kind of a linear increasing ramp, but here in C with accelerational control is kind of a nonlinear increasing ramp function there, right? So what tends to happen is that because you overshoot it, then you have to perform another control input in the opposite direction. And that's what we're seeing down here in graph E, is that the initial shift one direction results in a slow laggy response that results in the person having to shift their board back down to another state, which then results in a laggy response, and the person has to do another input. So the person is constantly doing this with their plank, right? And the same would be true of my controller using a button to control my rocket ship, right? The idea is that I'm hitting the button too long and then it's accelerating. So then I have to pull on the brakes or fire a counter rocket, right? To slow it down, but I've done that perhaps too long because again, the system is slow and laggy. So I don't know how long to hold down my button, either when it comes to accelerating or decelerating the ship, right? So it gets hard. There's lots of overcorrections and oscillations and instability in these kinds of second order systems. So what does this teach us? Well, it teaches us that we should try to avoid second order control systems in control dynamics when we can. And if we can't, maybe we need some help, right? So in this situation, one possibility here is that maybe we want to avoid control loops altogether, right? Maybe I don't want to have a feedback loop here. Maybe I want a purely feed forward system that is perfectly calibrated, so I know exactly how much time I hit my button, and that always results in a perfect output to my acceleration of my rocket ship, and I never make a mistake. Well, that might be something that is achievable with a high level of expertise and experience and practice and training, right? And so with that kind of level of expertise, maybe we can work on a feed forward type of a situation where I just don't make very many mistakes. But we can't count on people being perfect, right? That's our lesson from the very first set of notes in this class. So we're going to have error. We have to detect and correct errors, and we need a feedback loop for that. So lower orders of control are going to be better when possible, but not necessarily all systems can be guided in a lower order of control, right? It might just be inherently the case that when controlling rocketry or large boats, that it is inherently a higher order of control, right? So can we change the control order? If we can do it, if we can reduce the control order, then we're going to try to eliminate that. Maybe if we can reduce lag, minimize control display gain, these things might be helpful. But, I mentioned a few things in previous notes before, right? What about a predictive display, right? So a predictive display is one that helps the operator predict the future state of the system before the system gets there, right? So imagine, for example, on my rocket ship now, instead of just holding the button down and hoping that I'm getting the right length of rocket firing to accelerate to the desired state, what if I also have a predictive display that automatically computes the future acceleration of my rocket based on how long I'm holding down the button? And if this is able to compute this for me, now I know when it's time to take my finger off the button, because the system is now allowing me to predict without needing to be an expert. The system is the expert in the sense that it has some ability to compute the future state of my rocket without me needing to know anything necessarily, right? On the other hand, we might automate this process entirely, right? Instead of just relying on an operator to hold down a button for some period of time, what if our operator simply just says, this is the future state I want the system to be in, and defines that future state, and then the system operates the appropriate controls automatically to get the system into that state. As an example of that, cruise control on cars works in a way that's similar to that, right? So if I set my cruise control, let's say 60 miles an hour, right? So I'm driving on the highway and I'm at 60 and I hit the set button on my cruise control, then I'm operating at 60, right? And it's going to maintain me at 60. But if I tap my brakes, what that does is it temporarily shuts off the active cruise control and allows the car to coast. But it still remembers that 60 mile per hour setting. And so if I have coasted now and I've dropped down to say 40 miles an hour, and then I re-engage the cruise control, what's going to happen is that the car will automatically accelerate back to 60, right? And I don't have to do anything, right? I can keep my feet off of the pedals at this point. So I don't have to worry about getting the car back to 60 myself. There's an automated process that brings the car back to 60. So that command state IC is now programmed into the system, right? It doesn't stay inside the operator anymore, but it gets programmed into the system, and the system can automatically return itself back to that state when instructed to. So here, automation could perhaps overcome some of these kinds of human error type systems here. Now, as I had noted, open loop is in theory possible when we just abandon the need and use of feedback, and we hope that our movement commands and our control inputs can always simply just be perfect. But that's the point here, is that it requires that kind of perfection. And maybe that can be achieved when we have people who are highly skilled, experts, and well-practiced. But that's not necessarily always a guarantee, is the idea here. I compare this to ballistic movements here. I have a cartoon just to wrap this up here. Right. The idea behind a ballistic missile, this is the difference between a ballistic missile and a guided missile, right? In a ballistic missile, you have a couple of settings, you set some angles and so forth on aiming your rocket. And then when you hit the button and shoot the pizza cannon in this case, right? Then the pizza is just going to go wherever you aimed it, and you're not going to be able to change its trajectory. But what you might learn is that you missed your target. So the next time you have to aim, you might make a slightly different adjustments to your controllers, right? And so over time, you learn how to best aim your cannon, and you become calibrated, and now you can do a very accurate open loop system. Assuming you're well practiced and well calibrated. But keep in mind that another drawback of this kind of open loop system is that even though it can potentially become well calibrated and the operators can become experts here, it doesn't necessarily account for those external disturbances, right? So if there's a stiff wind blowing when they shoot their cannon, even though it might have been perfectly aimed for a certain situation where there's no wind blowing, now you throw in a crosswind and now all bets are off. So even though that system works, it only works in a narrowly constrained, unless of course our operators become even more expert, right? So now if they say, okay, in zero wind conditions, this is how we aim it. But if there's a crosswind that's 10 miles per hour, now I have to do this modification to my aiming. And if there's a crosswind in the other direction, 25 miles an hour, now I know exactly how much of a change, right? But the complexity of this becomes pretty drastic, right? And so we can see that these kinds of systems would only work in a very limited range of ideal, well-trained, well-calibrated type systems. In most cases, backing up here, we would have to rely on a closed loop kind of system that allows feedback to correct for these errors, right? And that's what guided missile is, right? The difference between a ballistic and a guided missile is that the guided missile is a closed loop, right? It may even be automatic, right? Where some onboard flight telemetry detects whether the missile is on target or not, and makes appropriate changes to its flight trajectory. And so again, though, we have to worry about the order of control and whether we're going to have a human involved in steering this or not, right? So that's ultimately the bigger challenge in tracking loops. And I just wanted to have that as to wrap up our human movement skill related topics.